Okay, take a seat, be quiet, please, and we shall continue. All right. So we covered some of the rules of probabilities for or, probabilities for and. We learned some of these rules. And we have more rules to learn. Yay! So
just out of curiosity, how many lectures will this one?
just one. Be done with it today. Okay. We have something called a conditional probability. So conditional probability is something we're already familiar with, except you might not know it as such. Okay? Knowing an aspect about someone gives us more information than just that one person, that one aspect. Okay? So if I say, all right, so just let's say we're playing a game. Okay, I've got someone standing behind this door. All right, this person has been randomly selected. What is the probability that this person is a woman?
50.
Around 50%. Okay, around 50%. If you know nothing about this person, and I just told you that this person has been randomly selected. Okay. All right. What if I say, okay, let me just give you one piece of information about this person. All right. This person is wearing lip gloss. Okay. All right. Now, so now we still don't know anything else about this person. All we know is that this person is wearing lip gloss. What would you say? What is the probability that this person is a female?
100?
So,
90 something.
okay, so we are, all right, so our answer has changed. We are no longer saying the probability that this person is female is just 50%. Just that one piece of information. I'm telling you this person wears lip gloss, okay? Now, lip gloss is not exclusively a female or male thing, okay? Are there men that wear lip gloss? Yes. Are there women that wear lip gloss? Yes, okay?
We don't see that many.
But-
I haven't seen that many men who wear lip gloss.
Right, but overall, if we look at the people who wear lip gloss, the majority, and I think it's very safe to say, without offending anybody, is to say that the majority of people who wear lip gloss are women, okay? So now if you know that the person behind the door is wearing lip gloss, that gives you an idea of what kind of person this is. And probably one of the things that you are now picturing is that the person behind the door is a woman. Okay? And so that is what we call a conditional probability. Okay? So let me just put that in equation form, okay? So when we know nothing, we might say the probability that the person is a woman, okay? We know nothing about the person who is randomly selected. Okay? So at that point, what's the probability that this person is a woman? 0.5. Now we add a piece of information. So to write this equation, to tell us, to communicate that we know that this person is wearing lip gloss, we change the form like this. We write probability that the person is a woman, but we say, I write a vertical bar and we call that given, okay? Vertical bar, basically saying, with this piece of information, wearing lip gloss, okay? So if we say, now that we know that the person is wearing lip gloss, what's the probability that this person is a woman? Making up a number. 0.93, I don't know. Okay. I just made up this number. The key being that it's no longer 0.5, but a higher number. So does that concept make sense? Okay, so when we know something, else, that could change what we know about this person, or what the other thing is. Okay. So in that case, so this is known as the conditional probability, okay? Because we are including a condition. The condition is this person is wearing lip gloss. So in generic form, we might say probability of B given A. So if we read this. Probability that A is true or has happened. I'm going to just slide this up. Oh, sorry. I want to leave this. Okay, so we're going to play the game again. So I've picked someone from this table at random, okay? We have no idea. And I say, what is the probability that this person is a man? Okay. If we know nothing about this person, we would write 90 divided by 170. And I don't know, we have something. 0.5294. Is that okay? Do we all get everything up here already? Okay. Alright, so now I'm going to put in a condition. Okay, so before we try to answer this question with a number, what is this thing saying?
It's a man kid.
Okay, so just if we say probability, we would say probability of man given conservative. Okay, so this is saying what is the probability of. Okay, so this is if we know. So basically the game is now, so someone's behind this door, and I'm going to give you a piece of information. That piece of information is that the person has self-identified as conservative. So in the survey, this person said, I'm conservative. What is the probability that this person is a man? Okay, so basically we're saying, if we know the person is conservative, what is the probability this person is a man? Alright. So how do we answer this?
35.
Yeah, so the answer is 35 divided by 59. How did I get that? Okay. Well, we're saying we know that this person is conservative, so we are limiting ourselves just to people in this column. Okay? If I say the person behind this door is conservative, we know it cannot be any of these people who identify themselves as liberal or moderate. Okay? So we are limiting ourselves to just these 59 people, and of those 59, how many are men? 35 of them. So our answer is 35 divided by 59. Is that okay? Okay, so just a very quick check. Don't shout out the answer, but try to think of this, okay? Alright, if I tell you that someone is a man, what's the probability that this person is moderate? So moderate, given. So write down an answer. Don't shout it out. We'll go over the answer in a moment. I'm not sure if who's working or who's stuck, or should I give you the answer?
Yes.
Okay.
33.
The answer, what is the answer?
33%.
Yes. 30 over 90 or 0.3333. Huh? Okay.
33, not 30, actually.
Oh, yeah.
Wait, what?
What?
Divided total mass
Okay.
by total moderate.
What happened here? What happened
I
here?
got mixed up with, I thought the bottom.
Okay, so some of you might have answered the other question, which is probability of man given moderate. So some of your answers might have been 30 divided by 56, which is a different answer. That's something else. 5357, okay? So some of you might have came up with that answer, but that is not what I asked. Okay? So make sure you understand the difference here. This one, what is the piece of information we know about the person? We know that this person is a man. And we want to know what is the probability that this man has self-identified as moderate. Okay? Well, there's 90 men total, and of those 90 men, 30 of them have said, I'm moderate. So that answer is 0.3333. Over here, the piece of information we know is that the person has self-identified as moderate. What is the probability that that person is actually a man? Or is also a man? That is 30 out of 56, okay? You've got to know the difference between this and this. Yes?
So for the first one, you always count the first one first, like moderate goes first because that's what the result has.
I'm not sure how. I don't know if I fully understand the question, so I don't know how to answer it. Basically, it's just the part that comes after the vertical bar is the part of information or piece of information that we know is true. This is the given information. and we're asking what's the probability of this. Okay, so that's what we're asking. We're asking what's the probability of this if we know this. Okay. Is that okay? Okay, so when we have a table, we have to be able to answer questions like this. Is that all right? Okay, do you guys need more practice, or is that good? One more practice.
Yeah.
One more. Okay.
Yeah, one more.
All right, so I'll put up a couple questions here, okay?
You can do it. Wow, keep messing with us. Just have to do it once, right? The woman with the liberal. Oh, yeah.
I might be wrong for the end section.
Did you get that? Because liberal, this is liberal total is 55. Oh, woman. Oh, right. I did the total. You're my two. Okay, so that goes. Okay, and then I do the second.
This is wrong.
Wait. Oh, you're right. I got you. I know what you're wrong. The total number of liberals is 55.
Yeah,
Did I do it backwards?
I think my way of doing it is wrong.
Total
This
number.
will be the total. Whatever comes second is the total.
Right, so the total liberals is 55. But this is how many women are.
Yeah, so
It's the same thing as this one.
this is liberal women.
Oh, it's 55. Right.
Okay, all right.
Oh, I got you. Out of it.
Some of you guys are still working. That's okay. All right. I appreciate everybody who attempted this. All right.
No,
Liberal and woman. Okay.
this.
What is the probability if I pick someone at random? Is any piece of information given here? Do we know anything about this person? No. There's no vertical bar here. So no piece of information is given. Okay? So just imagine someone's behind the door. I say, I picked someone at random from our table. This person's standing behind the door. What's the probability that this person is liberal and a woman?
30 over 107.
30 out of 170. 30 out of 170. Because we don't know anything about this person. So the answer here is 30 divided by 170. Is that okay? All right. What about this one? Same thing. Okay? No piece of information is given. All I'm saying is somebody standing behind the door, that person's been selected at random from our table. What's the probability that this person is a woman and liberal? Same answer, 30 out of 170. Okay? So here, there's no given information. Yes?
So we're just literally finding
30.
what lines, lining up the columns.
Exactly.
liberal
Out
and women.
of the total
the
number of
total?
people possible.
Okay.
Yes.
Is it possible for the question to be liberal or women?
Yeah, it could be, but that's not what was on there, right? So
I
if
know,
it was
but-
liberal or woman, that would be 105 out of 170. Okay. Don't worry about it. This one, liberal given woman. Okay, so what is the piece of information we know? Someone standing behind the door. What do we know about this person?
They're a woman.
It's a woman. Okay, it's a woman. What's the probability that she has identified as liberal? 30 out of 80. Great. Okay. All right. And in this case, someone standing behind the door. What do we know about this person?
The liberal.
That person is self-identified as liberal. What is the probability that this person is a woman?
30 out of 55.
30 out of 55. Great. Yay?
Yeah.
All right. All right. Okay. You got to be able to do this. All right. You'll see something like this on the quiz next week. Okay. You'll see a table, and then you'll have not liberal and women, but something, 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 and you got to be able to keep these straight. Okay. Yes.
For the quiz, will you give us like a graph like that?
Yeah. You know, if I gave you a quiz and I didn't include these numbers, can you still do the answer?
Yeah.
Yes. All you have to do is add up the columns, add up the rows, all right? I promise you, you can do it, all right? All right, right here. All you have to do, all right, if you don't have the total columns, all you have to do is make the total columns, okay? That's very easy. How do I get the total here? I do 25 plus 30, 55, okay? This plus this is this.
Are you sure of that?
I'm sure, yeah. We'll be okay. We'll be okay. All right. Here. All right. Well, let's try. We'll make a new one. Okay. We'll make a new table, and we'll talk about our next topic.
Don't get smart in this. You're just gonna click right now, right? Click, you get a whole new one. You get a whole new
All right. Okay. I'm trying to think of some situation here. Okay, let's say we have left-handed people right-handed. Okay, so we'll say, you know, which hand do you use most of the time to write with, okay? So, I know there's ambidextrous people, but even the ambidextrous people, I think, prefer one hand over the other, okay? So we'll just say, do you prefer writing with your left hand or your right hand?
Right.
And then we'll also ask, do you wear glasses? Glasses or corrective lenses, or, you know, glasses, contacts, whatever you want to call them, okay? Contacts, glasses, or no contacts or glasses. Let's say we have,
Go righties.
oh, I was not supposed to do this. Alright, okay, so this is your, here's your table, alright? And then here are the questions I want you to answer.
So conceivably,
Is this okay? Okay, so go. Another section to cover, so I'm trying to figure out the timing here. I might have to go over it. Did you get it? High five.
I got it. Well, I'm proud of you too. You helped me relearn.
All right, are we ready?
Too many pockets.
I'm gonna count in my head,
To a random prime number.
and I'm done counting. Okay. All right, let's go over the answer. We have another section to cover, so I just want to make sure we have enough time for that. Okay. All right. So to answer this, we have to create our total columns. Okay. So we just do this plus this, and we get that, and I do this plus this, and I get that, and I come over here and I get that, and I do this, and I get. Okay. So far so good. All right. So I want to know what's the probability that someone is left-handed. So I just do, how many people are left-handed? 35 divided by 245, and I get 0.1429. Everyone's happy?
Yes.
Okay. And then we say, what's the probability that someone's left-handed and wears contacts or glasses? Okay, and the answer here, 20 out of 245. And I get this. Okay. And given that someone wears contacts or glasses, what's the probability that this person is left-handed? 20 over 140. Okay. So this illustrates a concept where we call the events are independent events. Okay. What does it mean for events to be independent? Independent events, okay? We've covered a topic called mutually exclusive. Mutually exclusive is not the same thing as independence. Don't get those mixed up. It's a common mistake. Independent events means the outcome of one event has no influence on the outcome of the other event. Okay? And we kind of see this here, all right? If we know nothing about this person, I don't know, I like drawing this thing. Okay, someone's standing behind the door. We don't know anything about this person. What's the probability that this person is left-handed? 35 out of 245. The answer there is 0.1429. Okay, I'm going to say, all right, I'm going to give you a piece of information about this person. This person wears contacts or glasses. What's the probability that this person is left-handed? Now that you know that this person wears contacts or glasses, what's the probability that this person is left-handed? Okay. Does your answer change? Huh?
Yes.
No, it doesn't.
No.
Okay? If knowing, all right, if I just say, okay, before you even look at the numbers here, I just say, okay, so what's the probability that someone's left-handed? You say, whatever, 14%, 14.29%. All right, hang on, I'm going to give you a piece of information. This person wears contacts, or this person wears glasses. Does that change your picture of this person here? No. What's the probability that this person's left-handed? It's the same as it was before. It's still 0.1429. Okay? So, in some situations, knowing something about the person kind of changes your idea of what that person looks like. Okay? So, before we said, what's the probability that someone is a woman? We said 50%. If you know that this person is wearing lip gloss, now the image that you have in your mind is that this person is most likely a woman. Okay? Alright? What's the probability that this person is left-handed? If we don't know anything about him, we say, maybe like 1 in 6, 1 in 7. Okay? Our numbers came out to be 1 in 7. Okay? If you know something about this person, let's say, if I tell you this person eats with his left hand, what's the probability that he also writes with his left hand? Okay, then it goes up. Okay, so that would be associated. But if I just tell you this person wears contacts or glasses, it doesn't change your answer. Okay, so in this case, the probability that someone's left-handed and the probability that someone wears contacts or glasses, those events are independent. Is that concept okay? So if knowing something about the person doesn't change your probability of the other part, then those two things are independent. Okay. So to formalize this, which we have this here already, okay? If events A and B are independent, then the probability of A given B is equal to the probability of what? A. Okay. So if A and B are independent, knowing that B has happened doesn't change our answer about whether A or not has happened. So the probability of A happening, whether or not B has happened, is just the probability of A happening, if A and B are independent. Okay? And so that's what we have up there. We say the probability of left-handed given contacts and glasses is equal to the probability of left-handed. Is that true? Yes. We have 0.1429 equals 0.1429. So left-handed and contacts glasses are independent. So on the quiz, I might ask you, are these two events independent? Yes or no?
Yeah.
And you'll be given a table like this, and from the table you have to decide. And what you will need to do is you will need to calculate the probability of A given B and compare that to the probability of A. And if they're equal, they are independent. If they are not equal, they are not independent. You have a question?
So even if they're like close, like let's say A given B is like 1.531.
So at this point, we're going to say if they're not the same, they are not independent. Okay? Later on in our course, we're going to learn what we call a statistical test for proportions. And that's how we can decide if close means same or different. At this point, we're just going to say if they're not exactly the same, they're not independent. So that's a good question.
Thank you.
All right. Are we feeling okay with this concept? All right. So our last bit, okay? Sometimes we have sequences of events, okay? Alright. So, you know, we might have event A and we might have event B, okay? And we can ask, what's the probability of A happening and then B happening, okay? And actually, we write this the same way. We say, what's the probability of A and B? Okay, but this is basically, what's the probability of A and then B? Well, this is equal to the probability of A times the probability of B given A. So it could be something like, let's say A is there's a storm, and B is your flight is canceled. We could say the probability that there's a storm tomorrow, okay, depending on the weather or whatever, maybe there's a 20% chance of a storm. Okay? We could say, what's the probability that a flight is canceled? We could just say that's like 2%. But what's the probability that a flight is canceled if there's a storm? What's the answer there?
100%.
Maybe we'll say 40%. Okay, so if there's a storm, maybe there's now a 40% chance of cancellation. Okay? So are events A and B independent? No. Why? Because probability of B given A is not equal to the probability of B. Okay, I know I wrote that the opposite way before. Okay, but it's the same. So these two things are not equal, so they are not independent. Okay. What is the probability? Okay, we don't know if there's a storm going to happen tomorrow or not. But what's the probability that there's a storm and your flight is canceled? Well, first we got to say there's a 20% chance that there's a storm. And if there is a storm, what's the chance that my flight gets canceled? 40%. So what's the probability that there's a storm and then my flight gets canceled? It's going to be 20% times 40%, and I get a total of 8%. Okay, so what is the probability of a storm and my flight gets canceled? This is going to be the probability of a storm times probability of a cancel given storm, or A and B and A. So this is 0.2 times 0.4, 0.08. There's a brief exercise in your book covering this topic. Okay. In other stats classes, they might deal with this more heavily, okay? They would have you calculate all sorts of other probabilities based on these things. In our class, we're going to tone it down, and this is as much as you need to know regarding that, okay? But this last topic, we've got to cover. All right, and we have to do probability of sequences of independent events. Okay. So if events are independent, then the probability of A and then B is equal to the probability of A times the probability of B. Alright, so just imagine a silly game. So in here there's 9 balls. 3 are winners. 6 balls. 1 winner. And have 10 balls and 2 winners. Okay, so we're gonna play a game. You go to a whatever, go on a game show. And this is called whatever, I don't know. Pick the winners, alright? So you're gonna it's the dumbest game, but whatever, okay, you mix up the bucket, you reach in there, you grab out a ball. If it's got a W, you go on to the next stage. You reach in there, and if it's got a W, you go on to the next stage, alright? And so to win the contest, you have to get a winning ball, keep going on to the next stage, and then if you pick a winning ball in the last bucket, you win the prize. Does that make sense?
Yeah.
What's the overall probability of winning a prize? So you've got to get through this one, and then you got to get through this one, and then you got to get through this one. So what's the probability that you're gonna win?
No chance.
It's tough, but it's possible, right? Okay. So we'll say we'll call this stage 1, stage 2, and stage 3. All right. What's the probability of win stage 1?
3 over 9.
What is that?
3 over 9.
3 out of 9. What's the probability we win stage 2?
1 over 6.
1 out of 6. And what's the probability we win stage 3?
2 over 10.
2 out of 10. Okay? Alright, so we can multiply all of these out, or you can leave it, and we can put it in decimal form, or leave it in fractional form. It doesn't matter. So what's the probability of winning overall? It's actually not too bad. It's 1 out of 36, but so we got it's going to be probability of win stage 1 times the probability of winning stage 2 times the probability of winning stage 3. Each stage is independent of the other. Okay? What happens in stage 3 is not influenced by what happened in stage 2 or stage 1. So all of these things are independent of one another. So we can multiply these things. So I do 0.33, 3 times 0.1667 times 0.2, or actually it's not 1 out of 36, it's even smaller than that. Alright, let's see. Yeah, 0.011111. You don't have to have that. Okay, so it's 1 out of 90 actually. Okay. Yeah, 1 out of 90. Is that okay?
Yeah.
Yes.
So you said they're independent variable, or they're independent of each other?
Yes.
But wouldn't you have to win? Doesn't it depend if you're gonna go on stage 2? Don't you have to win? Doesn't that depend on if you're gonna win stage 1?
But what happens, whether or not you win stage 2, does not depend, is not influenced by what happened in stage 1. So let's say, let's say there was some other game where you're just gonna pick balls from all 3 stages no matter what. Even if you lose stage 1. Okay, but to win the grand prize you have to win all 3. Okay? Then what's the probability that you win stage 2 where you win movie tickets? That's 1 out of 6. Okay. Alright, sorry. I know I'm running over. Okay, let's say we just kept playing stage 3, okay? So let's say we played stage 3 4 times, okay? Okay, each time you draw the ball, you see whether you won or not, you put it back in, you mix it up, and you draw the ball again, okay? So every time, what's your probability of winning? 0.2, okay? Because if you put the ball back and we mix it up again, the probability of winning is always going to be 0.2. So what's the probability we win all 4 times? Okay, so maybe in your notes, put the answers on another page, and that way you can go check yourself for understanding here. And because I would love to do it where we test you guys, but we're gonna run out of time. Okay. So on the next page, the answer here is going to be probability of win times probability of win that's so put that in your notes on the next page and try. So this is just every time you play the game, your probability of winning is 0.2. If you have questions about this, ask away on Facebook. I'll be happy to try to answer. Okay. And then another one. All right. What's the probability we lose all 4 times? So put this on the same page as the question, and then on the other side, the answers, okay, it's going to be probability of lose times probability of a loss. Slide this up. So put that in your notes. And you know these are hard and tricky, so study them, okay? See if you can answer without looking at the answer, and then if you get stuck, look. And if you have more questions, and then one more, all right? I know some of you guys are packing up, and I apologize for going over, okay? Yes? Probability of a loss is 1 minus probability of win, which is coming from our complement rule, okay? This is what I like to hear, okay? Winning at least 1 time out of the 4 games, okay? This is equal. possible outcomes. Yes. 5904. Oh, 5904. Oh, yeah. Sorry. Thank you. Okay, so write that down in your notes. I know I didn't explain very well, or a lot, okay? But I do believe if you read these and look at these carefully, it will make sense. And again, if you have any questions, post your questions on Facebook, or if you don't have Facebook, send me an email.
You did have questions?
That should happen.
The quiz?
Yes, so you might see some sequence of events on the quiz also.